Hey everyone, in this lecture I'd like to talk a little bit about distance in three-dimensional space. So let's start by drawing some axes here. We'll draw our x, y, z axes. Remember, the x always comes out of the screen. This is coming out of the screen toward us. Then we have y and z. And we would like to take a moment here to measure the distance between 2 points. So let's say we have one point here, P, and let's put another point here, call it Q. And we want to try to measure the distance between these points, and the distance will be the length d of this line segment that connects these 2 points. So the first thing we need to do is think through how can we even describe the distance of these 2 points. So the first thing we can do is we can write down the coordinates, right? So this point P is x1 units in the x direction, and then y1, z1. All right, and this point Q, and by the way, this is all three-dimensional. You have no depth perception, right, on a two-dimensional screen. So you just kind of have to use your imagination here, but this is x2, y2, and then z2 for point Q. And we want to try to measure the distance here. So the way that we're going to do this is break this down into component parts. So what do I mean by that? Well, the first thing I want to do is I want to move from this point P in the x direction from the x component of P over to the x component of Q. All right, so in my mind, I'm going to pretend that this point Q is out of the screen toward us, away from the point P. And let's say that we have to go this far. Okay, and so this right here, this little line segment goes from x1 out to x2, and the distance, the length of that, we'll call delta x. So this delta x is the difference here. In this case, it's x2 minus x1. Larger minus the smaller. So that's the length of this little segment here. Now, from here, we need to do the same thing, but parallel to the y-axis, right? So the next thing I'll do is go parallel to the y-axis over to, say, here. And maybe this is our y2. And, of course, this would be our y1. And this distance is exactly delta y, the change in the y between these 2 points. So y2 minus y1. All right, and before I continue, you can now imagine connecting these 2 points, right? So the idea here is that this point right here, this magenta point that I've just drawn, should sit directly below the point Q. Now, does it look like that? I don't know. I mean, I'm drawing this. You have to use your imagination a little bit. And so I want to know what's the length of this segment, this magenta segment. Well, look at what we've done is we've created a right triangle here. And the two segments that we've described the length of, those are the lengths of the legs of the right triangle, right? And so by the Pythagorean theorem, we can compute the length of this magenta thing here. I'm going to call it r over here. All right, so by the Pythagorean theorem, we have that r squared has to equal the length of this gray edge, delta x squared, plus the length of this one squared, right? So plus delta y squared. Or the other way we can say this, it's a length, right? So r is equal to the square root of the sum of the squares. So the square root of delta x squared plus delta y squared. All right, so that gives us our magenta length. From here, we have to go straight up to this point Q. And so the idea here is that this one goes from, say, z1 up to z2, right? And so, of course, that length, we're getting used to this, right? Now we know that this length is delta z. Delta z is the difference, z2 minus z1. And how are we going to compute the length of d now? Well, now we notice that d is the hypotenuse of a right triangle. And, of course, the right triangle now has legs of length r, and then this orange one of delta z. So we can apply the Pythagorean theorem one more time to figure out this length d that was in question, right? And so once again, by the Pythagorean theorem, let's give credit here to Pythagoras. Pythagoras tells us, right, that d squared is equal to the sum of the squares of the legs. So r squared plus delta z squared. All right, but we know exactly what r is, so we can plug in all of this right here for r squared. And so this becomes the square root of delta x squared plus delta y squared squared, the whole thing, plus delta z squared. Okay, and then obviously when you square a square root, everything here is positive, so squaring a square root leaves us with just the sum of delta x squared plus delta y squared plus delta z squared. All right, and so what does this tell us? Well, remember d is the distance between our points, right? So what we end up with is a formula for the distance between P and Q, these 2 points whose coordinates were given, and we have to square root everything, right? So we get that the distance formula is the sum of the the square root of the sum of the squares of the component-wise differences. So delta x squared plus delta y squared plus delta z squared, all under the square root, and that's our distance formula, right? But we can do better because we had coordinates for these points. P and Q had coordinates, x2, x1, y2, y1, and we even wrote down what they equaled, right? So we can substitute out these delta symbols with exactly the differences that they equal, and we get our distance formula here. So PQ can be written as the sum of, or the square root of the sum, x2 minus x1 squared plus y2 minus y1 quantity squared, finally z2 minus z1 quantity squared. Like I said, square root the whole thing. So that's our distance formula right there, derived by a couple applications of the Pythagorean theorem. In reality, what we got there was like a 3-dimensional version of the Pythagorean theorem, right? So this is like d squared equals the sum of delta x squared plus delta y squared plus delta z squared. That is like a 3-dimensional version of the usual Pythagorean theorem. Okay, well, what do we want to do one application with this before we move on. So this is our distance between 2 points. You guys may remember that if you wanted to define a sphere is a set of all points in space, right, that are equidistant from a fixed point. All right, so the idea here is that we fix a point, call it C. We fix a distance, call that length rho. This is a Greek letter rho here. I'm using this letter because this is what we're going to use moving forward. But fix this letter rho, and then as you allow this point, if you keep this like this line segment fixed at the point C and let the other point move around, what it'll do is it'll trace out this entire sphere. So the sphere is equal to what we call the locus of points in space. When we say space in this chapter, we mean 3-dimensional space, and these points are all equidistant from the fixed point C. Equidistant means the same distance from. So these are all equidistant from C, right? And so that means that if we pick some generic point here, let's call this generic point P. It's a good name for a generic point, right? And just give it generic coordinates, x, y, z, in space. Then this means then that the distance from the point P to the point C has to equal rho, right? And we just found a formula for the distance. So let's say that our center point here, C, its coordinates we'll call h, k, and l. This is standard, right? And then what we know is that the distance from P to C has got to be equal to rho for all points P on the sphere. All right? We can do even better than this, though, because we know that if these are both positive numbers, right? They're both distances. So we can get then an even better formula, or just it's nicer to look at, by squaring both sides, right? So we can square both sides. And what we end up with then is that the distance squared, so we go back to our distance formula. If you were to square this, you would just cancel out the square root, right? So that's good. But our distance squared has to be equal to the radius squared. And so what we end up with then is that the sphere with center at this point C, h, k, l, and radius rho, radius length, right? Radius length rho is given by, right? It's given by this formula. So the distance squared is just going to give us what? X minus h squared plus y minus k squared plus z minus l squared. I'm just taking our distance formula applied to these 2 points. We don't need the square root because we squared it. And what does it equal? On this side, it equals rho squared. All right, so this is the equation of a sphere with radius rho centered at h, k, l. All right, well, let's use this formula. Here's an example. We want to find the radius and the center and the radius of the sphere given by this formula. So this says x squared minus 8x plus y squared plus 2y plus z squared minus 4z plus 17 equals 0. This does not look like the form that we just wrote down, right? This looks a little bit different. So what do we have to do? Well, we have to get it in that form. So what I'm going to do is I'm going to write down, I'm going to leave some room here. So I'm going to write down the first couple terms, x squared minus 8x, leave some room, plus y squared plus 2y, leave some room, plus z squared minus 4z, leave some room, equals, and at this point I'm going to move this 17 to this side. But how do I do that? I have to subtract it, right? So on this side, I end up with a negative 17. And for each of these, if we go back and we look at our formula, scroll down, look at our formula here. We need to basically complete the square on those three terms that we have on the left-hand side. And when we do that, we're going to get some constants that we'll have to add to the right-hand side. So let's go back and check it out again. We need to complete the square on each of these, right? So we need to complete a couple or three squares and balance the equation over here, right? So remember how to complete the square. You have to take this middle term, call it b, divide by 2, so I'm going to make a list over here. b is equal to negative 8. b over 2 is equal to then negative 4, and b over 2 quantity squared is equal to 16. You should know how to complete the square, so if you need to review that, definitely take some time to review it. But for the sake here of this argument, I'm just going to very quickly plug these in, right? So we need a plus 16 for this to be a perfect square. But if this is 16 over here, if I'm adding 16 to this side, I'm going to have to also add it to this side. Okay, so I add it to both sides. And then the whole point is that this now factors as a perfect square of x plus this middle number now. So x plus negative 4 or x minus 4 quantity squared, right? And then we're going to do the next one. So you just do this for all of these. Half of 2 is 1. 1 squared is 1. Add 1. Both sides, right? Same thing with the last one. Half of negative 4 is negative 2. Squared is plus 4. So plus 4. All right. And this one factors to be y plus 1 quantity squared. This one factors to be z minus 2, right? Z minus 2 quantity squared. And on this side, look what happens. We have negative 17 plus 17 is gone. All we're left with is 4. But 4 is a positive number, right? And so at this point, this looks just like our general formula for the sphere. And we can now extract the center and the radius, right? So the center is the point, right, whose coordinates are the opposites of these numbers. So it was always x minus h, y minus k, z minus l, right? So this is going to be 4, negative 1, 2 for the center of this sphere. And the radius rho is the square root of this number. So the square root of 4 is 2. And so this is this equation right here that we were given represents the sphere centered at this point, 4, negative 1, 2, whose radius is 2.